Hello students, how are you? Today we are going to be talking about the design combination of a digital circuit. It says an engine has 4 field sensors and the engine should keep running unless any of the following condition arises. What this means is that the engine will have 4 sensors and these 4 sensors will only be activated if any of the following conditions arises. So basically condition number 1 says if sensor 2 is activated. Condition number 2 says if sensor 1 and sensor 3 are activated at the same time. And then condition number 3 says if sensor 2 and sensor 3 are activated at the same time. And condition number 4 says if sensor 1, sensor 3, and sensor 1, 3, 4 are activated at the same time. So basically what this means is that the engine will have 4 sensors, and unless any of these sensors are activated based on the conditions, then basically the logic gate, the engine will stay on. So if any of these sensors are activated, then the engine will go off. So for this example, we will represent a 1 for a sensor being on, and we will represent a 0 for a sensor being off. So let me just write it down here. A 1 would be sensor on, or a 0 will be sensor off. So basically what you want to do first is you want to start out and write down the logic table here. And this logic table, since you have 4 sensors, you're going to say 2 to the power 4, which is equal to 16. So that gives you the amount of binary bits that you need to represent these sensors with. Seeing that it's a 16-bit, we write it down here in the table with our sensor 1, sensor 2, sensor 3, and sensor 4. And we have our Y as our output. So we are just going to fill in this table with binary numbers. And that's basically easy. You just start from the first sensor, which is sensor 4 on the right hand side, and you fill in 0, 1, and you end up doubling the numbers. You see what I mean here. So this, you fill in 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. And then for the second row, you basically double. So it should be 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. And you do the same thing. So it's 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So good. Now that we have our sensors, our binary table filled in, it's time for us to get to fill in for the conditions. So basically, I'll be using a different marker, but here are the conditions. It says if sensor 2 is activated. So we come down to sensor 2 here, and if it's activated, basically meaning that is a 1, then we write our Y output as 1. So if sensor 2 is activated here, you can see that sensor 2 is activated. So our whole sensing system will activate. Similarly here, it will also activate. And then we go on to condition number 2. It says if sensor 1 and sensor 3 are activated at the same time. So we come down to where sensor 1 and sensor 3 are activated at the same time, and you can tell that it is here and here, and you already have 1, so it is already represented, so we just mark it off. And then our other condition is that if sensor 2 and sensor 3 are activated at the same time. So we come down to sensor 2 and sensor 3. If they're activated at the same time, then we represent it with a 1, like here, 1, 1, and that's it. So sensor 3, condition number 3 has already been proven to us. Now we come down to condition number 4, which says if sensor 1, 3, and 4 are activated at the same time. So sensor 1, 3, and 4 should be activated at the same time, and it's only here. So we represent that with a 1 basically. So 1, 3, and 4, 1. Also, where else do we have conditions being met? 1, 2, 3, 4, 5, 6, 7, 8, 9. Also, we have another condition here. I think I skipped the condition. Here, if sensor 1 and sensor 3, sensor 1 and sensor 3 is here. So now that we have satisfied the conditions, we put zeros elsewhere. So now we want to represent the output basically with the representation of Karnaugh maps. So you are just going to write down your Karnaugh maps, and it's very easy. Let me just show you here. And you write down the Karnaugh maps in a 16-bit. So you still represent them in a 16-bit in order for you to get your accurate answer. So here I'm just formulating my Karnaugh maps, and you know Karnaugh maps is always represented with sensor 1, sensor 2, sensor 3, sensor 4. And your Karnaugh maps is always represented with it's not binary but BCD numbers. So basically you write it down in BCD numbers. So here you have 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, and 1, 0. So you come down to the condition that is active. So the first condition here on the output, which is Y, is only if sensor 1, so if sensor 1 is, sensor 2 is on. So we read it as 0, 1, 0, 0. So it's 0, 1, 0, 0. So we put a 1 here. And then our next condition is 0, 1, 0, 1. So it's 0, 1, 0, 1. Another one there. And then our other condition is 0, 1, 1, 0, 0, 1, 1, 0. See here? And then our other condition is 0, 1, 1, 1. So it's 0, 1, 1, 1. And then our other output is 1, 0, 1, 0. So it's 1, 0, 1, 0. So it's here. The other one is 1, 0, 1, 1, 1, 0, 1, 1. Our other condition is 1, 1, 0, 0, 1, 1, 0, 0. So it's here. Our other condition is 1, 1, 0, 1, 1, 1, 0, 1. And then our other condition is 1, 1, 1, 0, 1, 1, 1, 0. It's here. And then our final condition is 1, 1, 1, 1. So basically, Karnaugh maps, you want to group as many ones as possible. And I'll have another video explaining Karnaugh maps for you. So the grouping process, I'll group it with a pencil here. You want to group as many ones as possible. So I'm going to start off with the grouping this group right here. Not sure if it's visible, but I'm going to group this speck of ones right here together, and then this speck of ones right here together, and then this speck of ones right here. So the Karnaugh maps, if you want to group ones, you must group them in multiples of 2 to the power n. So basically 2 to the power n. So that's how you group the amount of ones that you want in Karnaugh maps. So seeing that we have grouped this, we are going to write down our final Y representation basically. So Y is represented by, if we look at this group right here, we can tell that our sensor 1 will be there and sensor 2 would be there, but our sensor 3 and sensor 4 will change, so we discard them. So sensor 1 and sensor 2 are there, but seeing that sensor 1 has a 0 and the number is represented by 1, we put a bar. So, but what we are basically doing is a sum of products basically. And then we add on for the second group, we see that our sensor 1 and sensor 2 will be there, but sensor 3 and sensor 4 will change. So we still have sensor 1, sensor 2. And then what will happen here is seeing that sensor 1 is 1 and sensor 2 is 1, we leave them as they are. And then we come down to the final group here. We can tell that our sensor 1 will remain the same, it will not change here. And our sensor 2 will change, so we discard it, so sensor 1 is there. And then we check for sensor 3 and sensor 4. Sensor 3 here will not change, but sensor 4 will change, so we only have sensor 3. And seeing that it's also 1 and 1, so we represent it like that. So here we have the final Y output. So this engine right here, represented by these 4 sensors, will only remain running unless this whole logic gate has been activated. Basically, this is how you are going to represent your diagram in when you draw your IC. Basically, now we are just going to draw the logic gate, and we are going to, when you have seen that we only have sensor 1, sensor 2, and sensor 3, those are the only sensors we are going to have. So we have sensor 1 here, sensor 2 here, and sensor 3. And seeing that we have bars on top there, sensor 1, sensor 2, sensor 3, seeing that we have bars on top there, we will represent them with XOR gates, basically. Sorry about that. So this is what we are going to do. And we are going to tap in from any of this. So we go down to condition number 1, we say sensor 1 and sensor 2. But sensor 1 has a bar, so we tap in from here, sensor 1, which has a bar right here. And sensor 2, right here. And it's passing through a OR gate, an AND gate, so it goes through an AND gate. And then we come down to sensor 1 and sensor 2 being ended, sensor 1 and sensor 2 being ended together. And then for the third one is sensor 1 and sensor 3. So we have sensor 1 and sensor 3 being ended together. And all these sensors, basically, they are going to be ORed at the end, and this would be our Y output. So we just bring them in here, and this is what we have. So when you are going to wire your IC would look something like this. It will have a dent here. It will have your input 1, input 2, output, input 1, input 2, output. So you are going to wire it basically like you see it here. So this is how you solve the problem on design of combinational digital circuits. Thank you. Welcome back to another video, and we are going to be talking about a 555 timer, and here is the question. So the question reads as follows. It is required to generate a square wave with 60% duty cycle. Now, using a 555 timer, design the required circuit for a square wave to have a frequency of approximately 50 kilohertz, and assume that the charging capacitor value is 2 nanofarads. So what this means is that you're going to design a 555 timer, and it will basically have a value of R1 and R2 that it will take in order for all the required parameters to be met. So for this we need to answer it, and here are the formulas that we are going to use. So the first formula is the duty cycle formula. The duty cycle formula, which I'm going to represent by DC, says the duty cycle is equal to R1 plus R2 all over R1 plus 2R2. And the other one is the frequency formula, which says that the frequency is equal to 1.44 all over R1 plus 2R2 over the capacitor, which is C1. So basically here, we are going to start off with the frequency formula, and we are going to make R1 the subject of the formula. So our R1 will be equal to R1 plus 2R2, which is equal to basically 1.44 over the frequency divided by, which is basically the multiplication of C1. And this is what we have basically. So we start off by substituting what we have, and we have got that R1 plus 2R2 is equal to 1.44 all over the 50 kilohertz, which is our frequency, times the capacitor, which is 2 times 10 to the power 9, and that is our R1 and R2. So R1 plus 2R2 is equal to 1.44 all over 50 times 10 to the power 3, all multiplied by the capacitor, which is 2 times 10 to the power negative 9, which gives us 14,400. So basically our R1, making R1 the subject of the formula, it's equal to 14,400 minus 2R2. So we come down to the other formula, which is the duty cycle formula, and we fill it in. So the duty cycle is 60%, so it's 0.6 is equal to R1 plus R2 over R1 plus 2R2. So basically, wherever there is R1, we substitute it basically with this formula. So we have got 0.6, which is equal to 14,400 plus R2 all over 14,400, minus 2R2 plus 2R2 minus 2R2. So basically for this formula, you can tell that R2 and this R2 in the denominator will cancel each other, and these ones will basically subtract each other. So our final formula would be 0.6 is equal to 14,400 minus R2 all over 14,400. So we multiply both sides by 0.6, I mean 14,400. So 0.6 times 14,400, which will give us 8,640 is equal to 14,400 minus R2. We make R2 the subject of the formula, which will give us 14,400 minus 8,640, which R2 will give us 5,760 ohms for R2. Now for us to get our value for R1, we just substitute R2 within R1. So R1 is equal to 14,400 minus 2R2, which is basically R1, which is equal to 14,400 minus 5,760, and our R1 would be 2,880 ohms. So when you're going to design your 555 timer, your resistor 1 should be of this value and your resistor 2 should be of this value in order for all these parameters to be met. Thank you.